Well, I want to thank the organizers for such a wonderful workshop. Unfortunately, I have to teach, so and then the time zone difference. So I couldn't go to many of the talks, but it certainly looked very good from what I saw. So today I'll be talking about the double copy in gravitational waves. It's the way that the double copy enters into our gravitational wave calculations. And this is work that I've done with various collaborators in the last couple of years. There's Clifford Chung, Radu Royban, the Jiaoshan Shen, Mikhail Solon, Mao Zhang. And then on spin, there's Andres Luna joined us. There's more recent work, there's Julio Parra Martinez and Mikhail Ruth. Let's see, who else I lost? Oh yeah, and then Dimitris Kosmopoulos also wrote a paper, recent paper on spin, which I'll just briefly comment on. Okay, so we all, I guess, are gathered here to discuss the question of gravity as the square of gauge theory. And I have to say I'm very gratified to see all the enthusiasm for this topic. So I can tell you what it was like when I first saw the KLT equation, the relation, the KLT paper. Nobody cared. And I was always very mystified by that, why nobody cared. But I have to say I'm no longer mystified because clearly people care. And that's really good. It's really something pretty amazing, something very deep about the way gravity and gauge theory are related. And not just gravity and gauge theory, but many other theories. And it's of course good to see so many people that I don't recognize them, all the young people. So that's a very positive sign. I think the young people know where the good stuff is. And there are, of course, many problems to resolve for which we've seen a lot of progress at this workshop. The underlying kinematic algebra, pushing the double copy to generic classical solutions, to have a generic way to write any solution, any physical problem, a classical solution, in terms of a double copy in gravity. And that of course, we don't know how to do yet, but we have many examples. And then also this idea is clearly being pushed very broadly to many theories, not just gravity. And one of the things that's driving the field is applications. So here I'm going to discuss one of the applications, how we use double copy for the gravitational wave problem. And of course, as everybody knows, the era of gravitational wave astronomy, it's begun. It's really fantastic. And I can tell you when I decided I was going to work on the problem, it's the day it was announced, I found out that the merger that they discovered, it was brighter in gravitational radiation than the brightness of all the stars in the visible universe are in electromagnetic radiation. That's pretty cool. And how can amplitudes and the double copy help out with the core mission of LIGO Virgo and also the future detectors? Well, that's what we'll discuss. Well, the first question is, what does particle physics have to do with gravitational waves? And they look quite different in particle physics. Let's say it's a Large Hadron Collider. We deal with gauge theories, QCD, electroweak, quantum field theory. Trajectories are unbounded. In general, in the case of gravitational waves, we deal with bounded orbits usually. There's general relativity, it's classical physics, and they look very different. But in fact, that's not true at all. It's just effective field theory. As long as we're dealing with a separation of scales, for example, long wavelength radiation, much longer than the size of the object, then we're good to go. They're particles, and we can then apply quantum field theory. And this was understood long ago and completely systematized by Goldberger and Rothstein in their seminal paper, and then many other papers that followed from a basic idea. So once we know that we can treat the black holes as though they were elementary particles, then the question is, okay, what can we do at the state of the art? We want to push the state of the art. If we're not pushing the state of the art on gravitational waves, then there's really no point in doing this. The general relativists don't need us. So it's so that's the key question. Now, how do we approach general relativity? Almost all people approach it, well, Einstein's equation, then geometry, and we all know all about that. But fundamentally, we think about it in a very different way. That's following Feynman. So the origin of, you could say, the way we think of like double copy and just think about the entire problem is we think about it as in terms of gravitons, that gravity comes from gravitons, spin 2 particles, and then we start thinking about how to understand those spin 2 particles in scattering problems. And this is the intellectual starting point for the double copy, that there are gravitons. Now, this is of course not suited for all problems. Formalisms are not meant to solve all problems. They're just meant to solve certain problems very well. And asymptotically flat space-times in the context of perturbation theory, that's a place where this idea is very good. Gravitons are very natural, and of course the double copy works very well. This is what we're going to apply here. Now, if you're going to use quantum scattering amplitudes, where we know all about the double copy, and you want to use it for gravitational waves, there's a few problems you have to deal with first. First problem is we're interested in classical physics, not quantum. So the question is, how do you do that? How do you make that transition from quantum to classical? And the other problem is the obvious one, that the scattering processes, they're unbound. Generally, LIGO has been measuring, or at least so far, it's only been measuring bound state problem. Right? So it's a different problem. And how do you go about converting from unbound to bound? And that's what we'll discuss here. What's the problem we're interested in? It's just the core problem of LIGO. There's 2 black holes. Here they are, it's black hole here, and they're inspiraling and they're radiating. There's gravitational waves coming off. Then they merge, and then the system rings down. The part that we're going to discuss is the in-spiral phase. For the other parts, you need different techniques, either numerical relativity for the merger or a different kind of perturbation theory for the ring down. For the problem of the in-spiral, the way we do it perturbatively is the way that it is used in LIGO. And it cannot be done by numerical relativity, at least not yet, for the simple reason that it's too expensive. Numerical relativity is expensive, and I mean literally expensive, money, computers, right? To generate the 250,000 templates, you just can't, there's not enough money. So we have to do it by perturbation theory. And perturbation theory is in fact the right tool. As long as the black holes are sufficiently far away, then you can use perturbation theory. There's ways of improving it, famous ways, effective one-body potential. That's a certain kind of resummation that allows you to get very close to the merger. And LIGO needs 2 inputs. They need the binding energy, that's by determining the Hamiltonian, and they need the frequency shift. For reasons of the way the radiation happens, the gravitational waves are always emitted, at least the ones that have been detected, from circular orbits. The orbits always circularize due to gravitational wave emission. So you only need binding energy. You don't, at least so far with the detectors, you don't need anything more than circular orbit. Just these 2 numbers is what LIGO Virgo needs. And the reason why they need it is because they can measure it. What this plot, I'm going to be pretty quick here, but what this plot is showing, the lower it is on the plot, the more sensitive it is. So if you're looking at it's called Post-Newtonian Approximation. In this Post-Newtonian Approximation, that's the orders of perturbation theory, you find that the detector is sensitive. It wouldn't be sensitive if you're off the top. For example, Hulse-Taylor binary pulsar is not sensitive to the higher orders of perturbation theory. but LIGO can measure it. And that's why we need it, because it's measured. And over the years, people have been marching up the orders of perturbation theory. The way this post-Newtonian approximation, which is not the one we're going to use exactly, but it's a standard approximation, is you just series expand. It's perturbative in Newton's constant. And if it's, especially if it's a circular orbit, then this is definitely true. V square is like GM over R. That's from the Virial theorem. So you do a double expansion in G and V. What you do is you calculate a two-body potential. First term is Newton. Next term of the potential would be Einstein-Infeld-Hoffman. That's one higher order in Newton's constant, or in velocity square. And this has been cranked out order by order, very high orders. And 2017, you can see 4 post-Newtonian. And the reason people do that is because it's needed. We need to go higher. And as high as we've gone, we've got to go way higher. And the reason is because much better detectors are coming online over the next 20 years. So we need to get the theory under the same control that the detectors will have. So when we started this, we were asking a question: what problem should we solve? There are a number of candidate problems. You can look at spin, finite size effects, new physics effects. You can study the radiation, not just the orbit itself. Or you could go to very high orders of perturbation theory. And we decided on certain boundary conditions on what problems we would solve. It had to be difficult using standard methods. It needed to be of direct importance to the general relativity LIGO theorists. If it wasn't important to them, then we shouldn't do it. And then it also had to be in a format such that, in principle, it can enter the LIGO analysis pipeline. Otherwise, we weren't going to do it. Anyway, there's an answer to this. High orders of perturbation theory, that's the one. We're also good at that from using, let's say, like in supergravity, we went to very high orders. So we're pretty confident we could go to high orders. The particular problem, which I'll explain in just a second what it is two-body Hamiltonian at the third and fourth post-Minkowskian order. And this was explained to us at Amplitudes 2018 by Alessandro Buonanno, who came and said, gave us our marching orders. This is what needs to be done. This is important. And with this plot, it's a little busy, but I like it because it's from her, apparently also from Justin Vines. But when you look down this table here, the zero post-Newtonian, that means Newton. So that's V square 1 over R. Well, 1 over R actually means G over R. So that's just Newton. This is Einstein-Infeld-Hoffman looking down this column, and then so on and so forth. And then you could see, for example, higher post-Newtonian, the unknown things here, like right here, this was an unknown coefficient. Now, when you look across the row, that's post-Minkowski. Post-Minkowski is the general relativist name for what we call perturbation theory. You're just expanding in Newton's constant, keeping all orders of velocity. We like all orders of velocity. It's Lorentz invariant. Why wouldn't you do it in a Lorentz invariant way? But in any case, it's become more popular for them, and it's definitely popular for us because naturally we like Lorentz invariant quantities. So there's what we had to do. That was our marching orders. The third post-Minkowskian, so that would be order G cubed. Order G to the fourth would be fourth post-Minkowskian. And also here's an invitation from Thibaut Damour, one of the leaders in the field. And how do you like this? In this paper, in the abstract, they say, we urge amplitude experts to use their novel techniques to compute two-loop scattering amplitudes of scalar masses from which one could deduce the third post-Minkowskian effective one-body Hamiltonian. So there's the invitation. It's very hard to resist this one because it's just laid out exactly what we needed to do. And also, this is an admission that it's hard for them to do, right? They're not inviting us because they can do it, right? So, or that it would be easy for them to do that. It looked hard to them, so they asked for some help. How do we apply? How do we do it? Well, of course, we use the techniques we use in QCD, in gauge theory, and N=4 super Yang-Mills, generalized unitarity method. Basic idea is, we've seen this many times in this workshop, recycle. You try to recycle. You find something simple at tree level, and then you try to recycle it to build higher loops. And there are the standard cuts. And then there's this generalized unitarity. We're in fact going to see exactly these plots or these diagrams we're going to see in the gravitational wave problem. Maybe one comment, I'm talking about loops, and gravitational waves are classical. So you may have heard, maybe they taught you this in graduate school, that loops are quantum. Well, they taught you wrong. That's just not true. Loops are where the classical pieces are. Certain pieces of these loops is exactly the parts that we want. In fact, the trees are completely uninteresting because those are lower orders of perturbation theory. Okay. But in any case, what we're going to use generalized unitarity, same formalism. Of course, we're going to use the double copy because we want gravity. If you want an tree amplitude, does tree amplitude have to plug into the generalized unitarity? Obviously, I'm going to use double copy. We have the KLT. That's the one version. It turns out, for technical reasons, it's important to actually use the other representation. The KLT one turns out, and this is a bit unobvious, it turns out that it's not the best way to do it, but it's still very compact to talk about. And general, in this talk, I'll show you the KLT way of doing it. And okay, I don't have to explain it to this crowd, but then the basic idea is we just get gravity tree from gauge theory tree. Gauge theory tree is very simple, and then we build up the loop amplitudes from the generalized unitarity. The other way is, of course, the BCJ way, which again I don't have to say very much about in this workshop. And the basic idea, again, we first put the constraints on the amplitudes. We organize the amplitudes so that at tree level, the kinematic numerators have the same Jacobi relations that the color factors have. And then once we've done that, then gravity is free, and we convert the gauge theory tree amplitudes to gravity just by this great substitution. Color goes to kinematic numerator, we're done. And then we do this for those tree amplitudes that we then plug into the generalized unitarity to get the loops. Yeah. Well, I guess I really don't need to say something. Oh, let me just say just a little side thing. Actually, I think one of the coolest parts about all this, it's not just gravity. So this was from our review. There's a version of that plot. These links, what these links refer to is, we could call it the single copy theories, that they share single copy theories. You find all sorts of relations between theories that you think should have nothing to do with each other at all, that there's just no possible way these things could be connected. But anyway, these things are all interlocked, all these different interesting theories, and including theories that are not gravitational ones. And I think that this is something really exciting and interesting, and this needs to be pushed as far as it can go. Now, the reason why we were pretty confident that we could do something for gravitational waves is because of this N=8 supergravity at 5 loops. And that's a pretty high order of perturbation theory. And just the fact that the double copy was extremely useful for this. It had to do with the problem of evaluating ultraviolet behavior in the supergravity theories. And this is an impossible calculation by superspace. I have no idea how you could ever get this high in order. As far as I know, nothing's been done beyond 1 loop for an extended supergravity like this using superspace. But these types of impossible calculations, they're now pretty standard. I mean, the rule of thumb is if you can do the calculation in gauge theory, you can do it in gravity. That's the simple message from the double copy. And that's what we use. How are we going to attack this problem of gravitational waves? Well, the attack goes by combining all the stuff we know from the amplitudes community, like the double copy and generalized unitarity and integration methods. And we combine that with the ideas from effective field theory in order to extract these two-body Hamiltonians, this post-Minkowskian potentials. Those are two-body Hamiltonians. The potential between two black holes, that's what we're after. The Hamiltonian, two-body Hamiltonian. And this is what our friends, the gravitational wave friends, that's what they asked for, two-body Hamiltonian. So that's what we produce by combining these two ideas. Let me just comment, this effective field theory methods, these days, there's much better ways of organizing the calculation, not using the effective field theory, but certainly every time we push into new territory and think about new problems, maybe it's spin or some other problems, we always go back to the effective field theory because it helps us get rid of confusion. We find it very useful. This effective field theory is very simple. It's literally here. It's so first there's particle A, that's black hole number 1. Particle B, that's black hole number 2. It's relativistic, but on the other hand, notice the kinetic term is linear in time. That's because there's no antiparticles, right? We're not exciting any anti-black holes here, so we just use relativistic not including antiparticles. Oops. And then the interaction is just the potential. This potential could be like Newton, and then the corrections to Newton. That's what we mean by the potential. And the idea is we use this effective field theory to extract the potential by matching. We match it to the full theory. The way the calculation goes is two parallel calculations. One is full general relativity. We throw all the techniques. We throw amplitude methods, double copy. We're taking h bar goes to 0, generalized unitarity. You want h bar, it goes to 0, so you throw stuff away that's you're not interested in. You throw it away quickly. And then what you do is you integrate it and you get an amplitude. The effective field theory, the way you do that is you build an ansatz for the potentials. You build the most general two-body potential that satisfies constraints like Lorentz invariance with some arbitrary coefficients, and you calculate in that. That's much simpler. You can just use Feynman diagrams. And then what you do is you declare that these two are identical. You match them. If you get a match, then you have the potential. Once you have the potential, you're good to go. You can then go to the LIGO theorists and say, here's a Hamiltonian. Okay, how do we do this? Well, we're living in double copy heaven, because what happens is you quickly realize, first, you're only interested in long range forces. If you're interested in long range forces, what that means is that the gravitons, the propagator has to be here. This is a graviton. It's interacting between two black holes. And that graviton, you have to have that propagator. If you don't have the propagator, it's a contact term, a short range force, not interested. So these two legs are effectively on shell because there's a propagator there. Then I think about it a little bit more and you say, well, we're going to go to the classical limit. And the way the classical limit occurs is you have to sit on the residue of the energy integral. The energy has to be localized. Remember, classically, Einstein's relation between energy and momentum holds. So therefore, you have to sit on a residue, and you can't have a free energy integral. So that means if you're sitting on the residue, you're on that pole. So you have 1, 2, 3 cut legs. So in the calculation itself, you are automatically on cuts. So that's unitarity heaven and double copy heaven, because it means we can just use KLT directly on these tree amplitudes without any trouble. If this would be this would be the first post-Minkowskian, and this would be second post-Minkowskian. First post-Minkowskian, this is essentially the only cut you have to do, unitarity cut. Third post-Minkowskian, it's 3 cuts that you have to do. And our tools fit perfectly. So let's have a look. So here I'm looking at the 2-particle cut. I mean, you can look at a sharper cut, but these cuts are so simple, you don't have to bother with that. So let's say you look at a 2-particle cut, and we can apply KLT to it. So there's a cut, a tree times a tree. And in the tree times tree, what we can then do is we can organize it according to KLT. So the trees factorize into Yang-Mills trees. And then you have to sum over the different helicities across the cut. And the way we control the spectrum, that there's only gravitons, is very simple. The graviton has to, in the factorization, has to have identical helicity, minus minus or plus plus. If I have a plus minus, it's not the particle I want. Then I get a dilaton or an antisymmetric tensor or axion, and I'm not interested in that, so I don't include it. So I project out the unwanted states very easily, and just use KLT pretty simply, keeping the helicity sums on these Yang-Mills tree amplitudes. I keep them, or gauge theory, I should say, since there's massive particles here. The gauge theory amplitudes, I keep these helicities correlated. If this is helicity H2, this one's also H2. Yeah. And that's how I do it. We can have a closer look at what it looks like. So let's have a look at gauge theory warm-up. So if I want to do gravity, maybe I should do Yang-Mills first, gauge theory. And we just go ahead and plug in the 4-point amplitudes, product of Comptons. There it is. I just evaluate that. And then we can just do a little gamma matrix algebra. And we get that the Yang-Mills amplitude looks like this. So E is what we call even piece. O is odd, but odd square. It's also parity even. So from a little bit of algebra, just evaluating these gamma traces, you can work out that the Yang-Mills cuts look like this. All the parity odd stuff cancels when I sum over the 2 different helicity configurations. And this piece here, it comes from identical helicities crossing the cut. This comes when the one is plus and one is minus crossing the cut. That's where this thing comes from. Okay, how do I do gravity? Well, answer is double copy. And you can see the echo of the double copy. This is identical helicity crossing the cut. I just square that. This was a square of the Yang-Mills, but I have to sum over the helicities. You can notice that this thing looks, that's 6. That's from the binomial theorem. This thing actually does look like a square, except all the odd pieces got canceled between the 2 helicity configurations. So we even see the double copy in this integrand, even though I've thrown away some of the particles. I've thrown away the dilaton and the axion. Okay, and this is, actually I may have said something right earlier. Maybe I counted wrong. This is 2 p.m. This is 3 p.m. counting. Okay. So then we can go to the next order. It's pretty much the same story at the next order. It's just the cuts are more complicated, but you find against similar structures. We can also apply the same idea. There's 2 other cuts, those are more complicated, but again, we can use KLT or BCJ on this one. Okay. And it turns out at the next order, there's technical reasons why the KLT one would be harder to use. But in any case, you have to now go ahead and integrate this. At this order, perturbation theory, there are actually many ways to do it. We didn't use high-tech stuff that was necessary for the next order. Basically, we did it order by order in velocity and just resummed. It wasn't that bad. Here's what the answer looks like once you integrate it. It's a relatively compact expression. Okay, it looks maybe a little bit complicated, not so bad, given that this is a 2-loop expression in gravity, extracted from gravity. It's in terms of, this is a logarithm, an arc-sinh. It's remarkably compact. These pieces here, they have to do with iteration pieces that cancel in the effective field theory. They're infrared singular. They're actually not so interesting. Okay. Now, what happened when we produced this answer? There was a bit of an uproar in the community because of this arc-sinh. People got confused very quickly about it because it has a mass singularity. And if you remember your general relativity in the scattering amplitudes, you're not supposed to have any mass singularities. So then, of course, that leads to a lot of confusion. The answer at the end is very simple. It works exactly the way you should have expected at first, and I'm not sure why there was that much confusion. You have to look at the real radiation. If there's a mass singularity, it cancels against real radiation, which is exactly what happens here. And there's basic theorems that guarantee that it has to happen this way. But anyway, that was a kind of fun thing that happened. Here's the two-body Hamiltonian. So this is the object that's desired by LIGO. Well, even something simpler is the binding energy for a circular orbit. That's what they really want. But anyway, the Hamiltonian is where you get it from, this thing, the potential. So this is just regular potential expanded in Newton's constant, and it's worked out to this g cubed order here. Okay. Now, when you do something like this, a very important question, not only for other people, but for us, is it right? We're doing it in this complicated way, I mean, it's like a different, it's a surprising, and you're coming at it from a strange direction, in that sense complicated. So how do you know it's right? The logic was all right. So of course, what you do is you compare against the literature. So people have computed to high orders, fourth post-Newtonian Hamiltonians. Their format is different from ours, but what we do is we series expand in velocity, and we match to them after a canonical transformation. It matches, therefore we know that it's like. But our friend Thibaut Damour, he was, shall we say, questioning the correctness of our result. And in fact, he was trying to correct our paper with specific corrections and said that we have the wrong answer and that the correct answer must be some other answer. And if you're curious what that was about, look at this paper version 1. I took this as an opportunity to get a nice bottle of French wine. So we made a bet. Anyway, the story is no problem. They did the calculation. It's actually quite delightful. So Damour calculates all the way to 6 post-Newtonians. So it's hard work to verify that our expression is correct. So anyway, I didn't get the bottle of wine because of the pandemic. Still owed the bottle of wine. And then there were many other ways of checking. There were many subsequent calculations, directly checking, other indirect checks of various kind. This question about the mass singularity, it's been completely resolved. Damour did a great job of resolving that completely. So we could now declare that the result has passed highly non-trivial checks and careful scrutiny from the community. So that's good. So what about the scalability? Okay, you did a trick, but how good is the method? Well, there's one way to answer that. Go to the next order. So indeed, that's what we did. It's the same story. I'm not going to repeat it, except there's more cuts. Again, use BCJ is used right here in each of these blobs. These are tree amplitudes. We just use it at tree level, feed it into the unitarity cuts, and then we have to integrate it. The integration is much more complicated. There's a great paper from Roof and Mao Zhang and Julio on how to do the integrals in an efficient way using ideas from QCD. So anyway, we need that in order to go to the next order. This is what the answer looks like. It's more complicated. Elliptic integrals appear. That's a slightly annoying, but not really a big deal. If Mathematica knows the function, you're good to go. Mathematica actually knows these functions, so no problem. And then you get also these logarithms, these arc cosh, that's essentially a logarithm. You get polylogs. There's a whole bunch of rational coefficients that I'm not listing. How do we know that's right? It's because Damour was very kind. Before we wrote our paper, he wrote a paper where he told us what we would find for the amplitude. So that was very nice of him, because he converted to our language and made a prediction what we would find in our language. And that's these coefficients here that he predicted, and we match those coefficients. So we are quite confident we have done it correctly. But of course, you can't do a calculation like this without some chaos and some arguments. So we disagree with, there's a calculation from Blumlein, Meyer, and Marquardt and Schaefer. It's a small disagreement, just one term, there's some issue. And that's at the 6th post-Newtonian order, that's very high orders. There's some issue that has to be resolved. And then there's another paper, after our paper, there's this paper from these people who have a similar result, except they say we dropped a piece. We disagree with that. In any case, this is a problem that I think the post-Newtonian people have to track down. There's disagreement in the post-Newtonian, and we're just caught in the middle of that. But in the meantime, we're confident we have it right. And within a year or so, we'll find out. I think the community will resolve this in finite time. Okay, here's actually something very nice. So that's a recent paper from Bonanno's group. And this is looking at scattering angles. In general relativity, of course, they're interested in that. Sooner or later, there will be events of black hole scattering and radiation that will be measured in some time in the future. And just to understand how we're doing, and in this plot, basically what you're seeing is that when you add higher orders of perturbation theory, you get closer to the truth. Truth is defined as numerical relativity, right? Because they do it exactly. Okay, they can't do every single process that's needed for generating templates that are needed in the measurement, but when they do one case, then they do it very well, and we can compare to that. So we're heading in the right direction. Now, this is in its raw form, where we just do perturbation theory, and okay, it's not so great, but now when you plug it into the professional, EOB, effective one body, that does a resummation in Newton's constant, and then you compare to numerical relativity. Now it's really awesome how well it does. So this is a really good sign. You know, they have a recent paper on that you can have a look at. A little more double copy before we finish off. There's a couple other examples where you can see nice double copy structure and problems related to gravitational waves. The energy momentum tensor is one place. This is the general energy momentum tensor for an arbitrary object, not just a black hole. If it's a black hole, these coefficients are 1. If it's some arbitrary coefficients, it could be a neutron star. And this is what the general energy momentum tensor of a spinning neutron star or spinning black hole. That's what it looks like. Okay, this I should say this is very closely related to the world line Lagrangian that people like Porto and Rothstein, Levy and Steinhoff have written down, except we do it in field theory. And say, okay, this looks nice. Does it have a double copy construction? Seems like a nice question. Suppose you have in a gauge theory, you have a spin. How do you what do you get? Anyway, the answer is double copy. It's exactly a double copy, and it works because these legs are on shell. You go off shell, try this in some specific gauge. Of course, it doesn't work at all. Here's another example of double copy. So this is from our paper. We're looking at spin. And we were looking at spin 1, spin 2 interactions and spin orbit interactions. You could ask, okay, is there something like a double copy? In fact, there is, and here's what it is. Our scattering amplitude factorizes into spin 0 times a spin s. There's an arbitrary spin. And it's in electrodynamics. Now, okay, what's electrodynamics have to do with the double copy? I mean, this has to do with the fact that we're actually doing it in Yang-Mills, but because the amplitude is pretty simple, it's just this Compton, that at the end, effectively, it's like being in electrodynamics. That's where the electrodynamics comes from. And in fact, like I say, it does have the double copy structure. What isn't understood is how to do this in general. We haven't worked all that out. Like for to get a complete double copy description for arbitrary spin. But anyway, this looks very promising, and I'm sure that much more will be done on that. So what's the outlook? The amplitudes methods, they have a lot of promise, and their use has already been tested in a variety of non-trivial problems. And I showed you how very directly we use the double copy and in order to do these calculations. It's been used to push the state of the art. So the calculations we did, it took about a year for them to be repeated by other ways. I mean, the name of the game always is to push the state of the art, and it's already been done. And we hope to continue doing that. There's other problems in radiation. There's a lot of work which I didn't speak about from many papers. There's a very beautiful formalism, I should point that out, that's called KMOC. There's Kossauer, maybe, and O'Connell. And then there's finite size effects. There's been a number of papers about that. Spin, there's quite a few papers, endless supply of papers on spin, and many more coming. Let me just make one comment about our last paper, which is a little bit surprising. So when you're describing a neutron star, there's a certain number of parameters. Well, in field theory, we call them Wilson coefficients. In general relativity, they might call them love numbers, or they would call them love numbers, Wilson coefficients. You can use whatever formalism you want, but you got to get the same number of Wilson coefficients no matter how you do it. Well, we have more Wilson coefficients than our GR friends, more independent ones. And the big question we have, is it physical, meaning that they, in a sense, do not have enough Wilson coefficients to describe the generic neutron star? Or is it technical in the sense that there's a certain set of constraints that we have not imposed properly? And we're not sure of this yet, but I think this is something very interesting, and you should stay tuned. In any case, what the punchline on this is, all the quantities of the standard quantities of interest, they can all be computed from scattering amplitudes. And I didn't mention a dissipative effects. I'm sure that could be done as well. So what's the summary? Double copy, it gives us a new way to think about problems of current interest in general relativity. Gravitational waves, it's a very good example of that. The double copy ideas have been used to push forward the state of the art. And we've pushed it all the way to order G to the 4th Newtonian-like conservative part. And also another thing which I didn't discuss here, just made a quick comment about it, is a re-examination of the basic assumptions about spin. So that's following from this way of thinking about things. I think best of all, whatever the methods we're using, they're nowhere close to being exhausted. We can see that we're going to go a lot further. We can think about higher orders in G, resummations in G, spin, finite size effects, radiation, dissipation are obvious paths. And I think in the coming years, we can expect many more advances, not only for gravitational waves, but also for understanding gravity and its relation to the other forces through the double copy. Okay, thank you.